Welcome to 6.1 Inverse Circular Functions. We're going to take a look at example 6. A, sine of the quantity, arctangent of 4/3 minus arccosine of 12/13. We are told to evaluate each expression without a calculator. Anytime we see an inverse of one of our trig functions, we want to have that be our theta. However, we have two. We have arctan and arccosine. So I'm going to go ahead and call these A and B. We're going to let A equal arctan of 4/3, and we're going to have B equal arccosine of 12/13. So now when we go ahead and look at this, this is going to equal the sine of arctan, which is A, and arccosine, which is B. So this is going to equal the sine of A minus B. So this will equal the sine of A minus B, which is our sine sandwich formula. So sine, cosine, sine is the pattern, AB pattern for both. And the sign will stay a minus. So now we know we'll need sine and cosine for both A and B. Those will be two separate triangles or two separate calculations. For angle A, first let's rewrite this as tangent of A equals 4/3. Since it's positive, it will be in the first quadrant. And we have y over x, so 4 over 3. 4 will be the y and 3 will be the x. And notice this is a 3, 4, 5. So we know that the radius is going to be 5 since that's a Pythagorean triple. If you weren't sure about that, you just solve using the Pythagorean identity. So now we can calculate cosine A is 3/5 and sine of A is 4/5. Now we're ready for angle B. First we can convert to cosine of B equals 12/13. So we already know cosine. And we either use a triangle or Pythagorean identities to get sine of B. Again, we are in quadrant 1 because it's positive. X over R, so 12 is our X, 13 is our R. And this is another Pythagorean triple. So if you're not sure of that, you would just solve 12 squared plus y squared equals 13 squared. But if you happen to know that 5, 12, 13 is a Pythagorean triple, then that means our missing leg must be 5. So our sine of B is going to be 5/13. Now we're ready to compute. We multiply straight across for both of these. We get 48/65 minus 15/65. So our final answer is 33/65. So again, the same strategy applies. Anytime you have an inverse in a composition of functions, you can let that inverse be a variable. And in this case, we had two, so we called one A and one B. Example 6B. Sine of 2 arccotangent of -5. So this is where you have to be very careful. When we go to identify our inverse function, we have to make sure we're only finding our inverse function. So we're going to go ahead and let theta only be this arccotangent. So we will let theta equal arccotangent of -5. So therefore, what we are looking for is not just sine of theta, it's actually going to be sine of 2 theta. So our equation for sine of 2 theta, our double angle identity, is 2 sine theta cosine theta. So now we need to calculate both sine theta and cosine theta. We'll do that over here. Because arccotangent is in the output of 0 to pi, and we have a negative here, we're going to be in quadrant 2. So we can rewrite this as cotangent theta equals -5 or -5/1. Since it's x over y, our x will be -5 and our y will be 1. Since we're in the second quadrant, we know that x has to be the negative and the y has to be positive. Now we will use Pythagorean theorem to calculate r. So 5 squared plus 1 squared equals r squared, or 26 equals r squared. R is always positive, so even though we get plus or minus rad 26 for r, when we go to our picture, we know r is positive, so it's rad 26. Now we can find cosine theta is -5 over rad 26, and sine theta is 1 over rad 26. Now, normally we would want to rationalize the denominator. However, I notice over here I'm going to end up multiplying sine times cosine, so we can save ourselves the hassle and just plug it in and see what happens. So 2 sine theta is 1 over rad 26. Cosine theta is -5 over rad 26. And notice the denominators end up getting rationalized themselves. So in the denominator, rad 26 times rad 26 is just 26, and the numerators will multiply. 2 times 1 is 2, times a -5 is -10, and this can be reduced to -5/13. So again, anytime we see a composition of functions, especially with an inverse, we have to identify the inverse alone, in this case just our cotangent, to be our theta. And then if we end up with a sine of 2 theta or anything with a 2 theta, we have to use our double angle identities. A, cotangent of secant inverse of u. We are going to assume that u is strictly greater than 0. This will guarantee that we're always in our first quadrant. So the same strategy applies where we first identify the inverse. So we're going to let theta equal secant inverse of u. So that means that secant theta equals u. Let's go ahead and draw that now. Again, u is positive, so we know we will be in quadrant 1. We can write u over 1. Since secant is the reciprocal of cosine, cosine is x over r, so this will be r over x. So our r will be u and our x will be 1, and we need to solve for y. So let's go ahead. 1 squared plus y squared equals u squared. This is just 1, so we subtract the 1 over. Y squared equals u squared minus 1. Now we'll do the square root of both sides. Y equals plus or minus square root of u squared minus 1. Because we are in quadrant 1, we're going to have just the positive square root of u squared minus 1. So now notice, look over here. We're trying to find the cotangent of the secant inverse of u, but secant inverse of u was just theta. So now we're just trying to find the cotangent of theta. Cotangent is x over y, so we're going to simply get 1 over the square root of u squared minus 1. Now we need to rationalize the denominator. Our final answer is the square root of u squared minus 1, all over u squared minus 1. Normally, when we have variables canceling out with our square roots, we have to be careful. We have to make sure that u squared minus 1 is not a negative. However, notice that your u must be bigger or equal to 1. So if the u is bigger, then u squared minus 1 will be positive. So our final answer is the square root of u squared minus 1 all over u squared minus 1. B, sine of 2 cosine inverse of u. We need to identify our inverse alone. So we will let theta equal cosine inverse of u. Converting that into a regular cosine, cosine theta equals u. So since the cosine is x over r, my u will be my x and my r will be my 1. we need to solve for y. U squared plus y squared equals 1 squared, or u squared plus y squared equals 1. Now we're going to subtract the u squared over. So we get y squared equals 1 minus u squared. Square rooting both sides, we get y equals plus or minus square root of 1 minus u squared. So the y, because it's in the first quadrant, will be the square root of 1 minus u squared. Now let's see what we're going to need from over here. Now we're going to replace the cosine inverse of u with theta. So we're really looking for sine of 2 theta. So using the double angle formula, we have 2 sine theta cosine theta. And remember, this picture is our picture for theta. So over here, let's figure out what sine theta and cosine theta are. So sine theta is y over r. So we get the square root of 1 minus u squared over 1. So sine theta equals the square root of 1 minus u squared. Cosine theta, we actually had from up here, or you can see from the picture, is u over 1, or just u. So now when we go to plug everything in, we get 2. Sine theta is the square root of 1 minus u squared, and cosine is just u. To write this nicely, we put the 2 and the variable u in front of the square root. So our final answer is 2u, square root of the quantity 1 minus u squared. I hope you enjoyed this video. See you next time.